Hi, my name is Andreas Geiger, and today I will show you some of our latest research results that we have obtained over the last 1.5 years towards the grand goal of self-driving systems that are robust and that can be trained end-to-end from data. There is two dominating paradigms currently. The first is the classic modeler pipeline, which decomposes the self-driving problem here in gray, which goes from the sensory input, tries to find a mapping to the actions of the vehicle through a decomposition of the problem into individual modules such as low-level perception, scene parsing, path planning, and vehicle control. And the advantage of such a modeler pipeline is that these modules are independent to some extent, so they can be developed by large teams in parallel to each other. And they are also quite interpretable because these representations have been designed by humans. However, this is also a disadvantage, as choosing the wrong model or choosing the wrong representation cannot be undone and has an adversarial effect on the overall system performance, as well as most of these systems assume that each of these models is trained in a piecewise fashion. For instance, there might be a module that's responsible for semantic segmentation, and then there's an auxiliary loss that says, well, I want to classify each pixel accurately with respect to its semantic class label, but that auxiliary loss knows nothing about the actual driving performance that we're seeking to optimize. So these are often quite decoupled. On the other extreme, there are end-to-end approaches where the mapping from the sensory input to the actions is implemented using a black box neural network that is trained using either imitation learning or reinforcement learning. And the advantage of such systems is that they are very simple. This is a system that is just composed of a generic convolutional neural network, for instance. They can be trained end-to-end for the actual driving task, for the actual actions. But on the other hand, they often don't generalize very well, and they are also less interpretable. And in this talk, we're going to focus mostly on the generalization aspect, but also a little bit on interpretability and trying to develop models that are both simple and can be trained end-to-end for the quantity of interest, but that at the same time generalize well, are robust to new environments, and can be interpreted better than existing models. The most successful approach for training end-to-end self-driving models is imitation learning. In imitation learning, we're given a set of expert trajectories that make up our data set. So we have always pairs, supervised training problem. We have pairs of input, sensory input or images, and actions, corresponding actions from the expert. So for every of these images, we know what the expert did. And then we can phrase this as a simple supervised learning problem where we try to optimize for such a policy that maps these images to the actions, and then run that policy at test time. And the advantage of such an approach, as already mentioned, is that hard coding policies is really difficult. So the advantage here is that we have a data-driven approach. We can train the entire mapping end-to-end from data, given demonstrations from a demonstrator. And we train this policy to mimic the decisions of this demonstrator. Yeah. So here's a diagram of one of the state-of-the-art imitation learning approaches called CLRS. Where you can see there's a driving policy that's conditioned on the camera and also the speed in order to determine how fast the vehicle is going currently. and then a navigational command that disambiguates ambiguous plans or ambiguous decisions at an intersection. This is a high-level command that tells the model, like a GPS system, at the next intersection go left, at the next intersection go straight, etc. Yeah, but the limitations of such an approach are that it doesn't generalize very well to new environments and has a high sample complexity, and it's also hard to interpret. So the first question that we asked ourselves is, well, how can we learn to drive under the vast diversity of all visual planning and control scenarios? Can we build a model that captures this better and more robustly than standard naive imitation learning with a single neural network? And this brought us to the idea of situational driving. Here I can show you some of the results of our method. You can see this is our policy driving in the CARLA simulator, which we use for evaluating safely our learned policies. You can see that it's quite diverse. There's different weather conditions, there's different or varying densities in terms of traffic participants. You have to conduct certain turns, need to yield to pedestrians, etc. It's quite challenging. Okay. We were inspired with this situational driving model by a paper called World Models from Ha and Schmidhuber. What they did is, in a much simpler environment than CARLA, this bird's eye view OpenAI gym environment, they trained a generative model of the appearance of the environment using a variational autoencoder here. So this is trained in a pre-training step. Then in the second step, we learned a dynamics model and a control model in the latent space, C, of that variational autoencoder. And then use that control model to actually perform the action. However, we realized that this is not sufficient when you take this approach and move it to the more realistic scenario of CARLA, which is a photorealistic self-driving simulator. And the reason is that this VAE is trained on a reconstruction loss that knows nothing about the actual driving task. So we're now combining, our goal is now to combine this idea here of optimizing the control using this evolutionary strategy with an imitation learner that learns a policy based on action and observation pairs from an expert. So here is an overview of the situational driving model. So given an environment and a demonstration in that environment, we train in a first step a mixture of expert policies via imitation learning. The difference to previous models is that here we have not only a single policy, but a set of K policies that we train together in order to arrive at a mixture output distribution. In a second step, we learn a context embedding for the environment as a beta VAE, similar to the World Models paper, where we at inference time then remove the decoder and just keep the encoder that predicts context embedding for from the input. And then finally, in a third step, we perform a task-driven policy refinement by interacting with the simulation and maximizing a driving task reward. So this is another RL step that is directly receives feedback from the actual driving task and refines the last layers of these neural networks of the context embedding and the expert policies. It's difficult to backpropagate with these very sparse gradients all the way through these networks, but because we have pre-trained both, and they give us very robust and diverse decisions already, this fine-tuning can actually be conducted at a very high level, only at the last layers. Here's a formal, here's our model more formally. So this is the driving policy. You can see this mixture model here. We have the mixture weights predicted by a neural network, and then the expert policies here. We have K of them. So it's a mixture of K expert models. And then we have this context embedding, which also includes aspects such as velocity or the navigational command. And that's simply a linear combination with a parameter vector that we train in this third step that I've shown you before. So this is our complete model. The mixture model here is a mixture of Gaussians. You can see that the expert policy is parameterized as a Gaussian distribution. So a Gaussian distribution over the action space, or a mixture of Gaussian distribution over the action space. And the action space is simply a two-dimensional space in the interval -1 and 1, which is representing acceleration and deceleration, as well as left steering and right steering. So very simple action space. And then for training, we follow these steps. In the first step, we learn a mixture of experts using a standard imitation learning log loss. In the second step, we learn the context embedding using a standard variational autoencoder, which is composed of a reconstruction loss and a KL divergence loss. And then we have our task-driven optimization, where we only optimize the readout layers, or the parameters of the readout layers, but now with respect to the actual rewards that we define for the driving task. So this is refining the overall system with respect to the actual rewards of driving. That's what we want to ultimately optimize for. Okay, so let's have a look at some experiments. We're using CARLA, the CARLA simulator, as a photorealistic and safe test environment. When we did this, when we developed these models, CARLA 0.84 was still the de facto standard, which was providing a training town and a test town. And we were training on the training town and evaluating on the test town. And the way this is done is that there's a random start and end location with a randomly chosen Weber, and then the metric that is measured is the percentage of successfully completed episodes. In other words, the success rate. This is the metric that was used in this first CARLA benchmark. And then in later and more challenging benchmarks, the metric has also been adapted to take more aspects like infractions into account. But in this first benchmark, collision does not necessarily terminate an episode. We consider different variants of this benchmark. We consider, for instance, a no crash benchmark, which is a harder variant compared to the original benchmark, as it varies the difficulty by changing the number of dynamic agents in the scene, as you can see here. So there's different scenarios where we have, for instance, empty scenarios, which is just static driving in static scenes. Then we have regular scenarios with around 65 agents per scene. And then we have a dense scenario with about 220 agents distributed over the town. And in this no crash benchmark, each collision immediately terminates the episode. So it's a much stricter evaluation metric. So there's also different Webers that we can generate using the CARLA simulator, and we have used that to generate a new benchmark to test generalization performance to novel Weber environments. Here you can see our training and test conditions. As you can see, they are quite diverse. Some of them are in cloudy environments, some of them are in bright sun environments, some of them have rain, some of them have direct sunlight that shines into the camera lens if you're driving towards the sun, etc. So we evaluate on 10 unseen Weber conditions in order to quantify the generalization performance of the approach. So the first thing we looked at is the importance of the mixture model. What you can see here is that in the static environment, already a single component model performed reasonably well on all tasks except for so this is the evaluation task and this is the training task, and the environment, you can see, performs reasonably well on the static environments. However, if we move to dynamic environments, so training and testing on dynamic environments, the situation changes. Now the performance on dynamic environments goes up, but at the same time, we are far from 100% success rate for all of these scenarios if we use a single component mixture model. On the other hand, if we use a model with 3 mixture components, we reach a significantly improved performance in terms of the success rate here. So in summary, the static model solves static scenes well, but cannot handle dynamic objects, which is not surprising. The dynamic model handles dynamic scenes better, but degrades on static scenes. And the dynamic mixture model generalizes to all scenarios. The next thing we looked at is the importance of the mixture model and task-based refinement. So in this case here, we have looked at 2 different variants of the model. One mixture of experts with a shared backbone, so shared weights, and one where we let the weights deviate for each of the backbones. And what we observe is that the performance improves up to 3 or 5 mixture component models in this case. So this is the baseline here, 75. But it doesn't improve further if we increase the number of mixture components further. And we also observe that separate backbones increase diversity and generalization. So the separate backbone version is better than the shared backbone version, which we attribute to the higher diversity in the models in this mixture model. And we also see that this task-based refinement, if we add it to the best version of the mixture models, we get another improvement of about 4%, which is a significant reduction in terms of error rate. What we can see here is what the different experts have learned for a particular example. And we can see that the acceleration distribution, which is shown here, is very different for the 3 different experts, which shows that the experts indeed specialize to different situations on different tasks, which is what we intended to do. So here finally are results on the CARLA benchmark, the official CARLA benchmark at the time, compared to state of the art. We see that this is a method that uses reinforcement learning, that standard reward-based optimization alone is not sufficient to get robust performance. LSD enables better driving. So LSD is learning situational driving, is our approach. Enables better driving behavior across all driving tasks. And we have a large improvement in particular in the case of dynamic objects, as you can see here in the last line. And the best performance is attained if we use our task-based refinement. So here are some results on the CARLA no-crash benchmarks. In this case, all methods perform worse because the task is just much, much harder. There's higher traffic density. There's more situations that are terminated just because of a collision that happened. And even the expert that is provided by CARLA and that's used for the imitation learners to train their models often fails in these dense environments due to clogging traffics situations. You can see that the expert in the dense environments often also gets stuck. However, we get pretty close to the expert performance in dense and empty environments. We see that LSD enables better driving behavior across all these driving tasks compared to these 2 baselines here. The state-of-the-art imitation learner and this is actually wrong here, the reinforcement learner. Here are some results finally on this new any weather benchmark, where we test generalization to challenging weather situations, and we can see that the performance of all methods decreases on these more challenging weather situations. However, again, we outperform the state-of-the-art method at the time, CARLA, in all tasks. Here are the different tasks. This is driving straight, doing one turn, multiple turns, and then multiple turns with dynamic objects. Yeah. But it's notable that if the weather situation is very difficult, then all methods can fail, even on very simple straight driving tasks, which you would think is easy to do. But the policies get easily distracted. Some challenging weather situations even lead to 0 success rate for all methods. And more research is definitely required to address these challenges. So here's some results. Let me show you this video. First, we see the state-of-the-art baseline CARLA, standard imitation learner. You can see that it leads to higher infractions like crossing the lane or running over a pedestrian, while for the same situation, the situational driver has adapted to the different situations through its mixture model, and also through its task-based refinement. Okay. Then the next question we ask is, well, how useful is data aggregation for self-driving? And this question is important because we're talking, in the case of self-driving, mostly about imitation learning, because reinforcement learning is just very difficult due to the credit assignment problem and the very sparse gradients. So this is one of the main reasons why imitation learning is still the dominating paradigm. But if you do imitation learning, then how should you do data aggregation in order to be robust to deviations from your policy? Right. It's an overview of the imitation learning setup that we've seen before. The goal is to train a policy to mimic the decision of a demonstrator. And the general imitation learning formalism is as follows. We are trying in the loop to minimize the expectation over the state distribution of the loss function of the predicted action with respect to the expert action. We're trying to minimize the parameters. Now, in this general imitation learning setting, the state distribution depends on the rollout determined by the current policy. And this is something that we cannot do in practice because we cannot roll out the current policy and query the expert for any possible state. That's why in practice, when we refer to imitation learning, what we actually mean is often behavior cloning, where we have almost the same formalism, but in this case, the expectation is over the state distribution provided by the expert. So this distribution does not depend on the rollout and the current policy anymore, but it's a fixed state and action distribution that has been provided by the expert demonstrator while driving and while doing its own decisions. So we have a fixed data set of observations and action pairs. That's the difference. And then, of course, it reduces to a supervised learning problem, and we can apply our standard machine learning machinery to it. However, this of course has problems. First of all, behavior cloning makes the IID assumption. It assumes that the next state is sampled from the states observed during the expert demonstration. And therefore, the next state is sampled independently from the action predicted by the current policy. However, of course, the policy might not predict the same action as the expert has predicted, in particular in the beginning of training. So, what happens if the learned policy makes a mistake? Well, we enter a new state that we haven't observed before, and then the new states are not sampled from the expert distribution anymore. Therefore, we might not be able to recover. We might diverge, and this might lead to a catastrophic failure or a collision, in other words. And for this reason, there are several data aggregation strategies that have been proposed, most prominently Dagger for data aggregation. And the idea is very simple. The idea is to iteratively build a set of inputs that the final policy is likely to encounter based on the previous experience, and then query the expert for the aggregate data set. So we take some data set from the expert and we train a policy. This is the data set from the expert. We use it for training a policy. And then we're rolling out that policy in the environment and make some new observations based on based on the environment that we have observed by following the current policy. So we have some new data now, which we add to the data set. And now we query the expert again for this new data that we have added to the data set and train the policy in the second step for the combination of the original data set and the newly annotated and newly captured data. And that way, over time, we observe more and more of the relevant state space. It's an excellent idea, and it has found widespread use in many manipulation tasks, but it hasn't been applied yet much to the task of self-driving. So we're wondering why, and if it also would work for self-driving. And what we found is that indeed, to some extent it works, but it can easily overfit to the main mode of demonstrations. So what I mean by this is that in self-driving, we have a very skewed distribution. For instance, there's a lot of examples in the data set where we're just driving straight and nothing interesting happens, just driving straight. However, the challenging and important situations are when we're making a turn, because many things can go wrong and everything is very quick. So we need to react very quickly in these cases. And so we want to actually make sure that these situations are covered well enough. And this is not what we automatically obtain with data aggregation, as evidenced by our experiments in the paper. And the other problem is that Dagger maintains the high training variance. That means if we choose a different initialization during training, different initialization of our policy, or we choose the order, we input the order in a different way during gradient descent, during stochastic gradient descent, we use different mini-batch orders, then we get hugely varying performance on the actual driving task, on the success rate, which makes it of course hard to evaluate and compare different driving models against each other. So here's an example of the skewness of the distribution. Here on the top left, you can see different commands that have been, or different settings, and a histogram over different settings for different weathers here. So for instance, these are situations where we are braking. These are situations where we're steering left, going straight, and steering right. And these are this is one of the data sets that we have used for training a standard CARLA imitation learner. You can see already that the distribution is very skewed. So for instance, braking occurs much more rarely than other situations. And this is already a de-skewed data set where we have manually tried to de-skew the data set. Now what happens if we use Dagger and iteratively adapt and extend this data set? Here's the first iteration, here's the second iteration, and this is the third iteration. And you can see that this skewedness of the distribution does not get alleviated. It remains there. Yeah, so the key idea of this work here is another work that we presented at CVPR in 2020, is to, instead of naively running Dagger, to sample critical states, important states from the collected on-policy data based on the utility that these states provide to the learned policy in terms of the actual driving behavior. And we propose some heuristics to do so. Right? And the second innovation we propose is to incorporate a replay buffer. And only in combination these two ideas work. That's what we found, because if you just sample critical states, then your model overfits onto the distribution of these critical states. But adding a replay buffer, which progressively focuses on the higher uncertainty regions of the policy state distribution, dampens this behavior and allows for proper training. So these are the two components that we have changed in Dagger. Yeah, so we, as already mentioned, we propose several heuristics. They are formally defined in the paper. Here, just at a high level, we have task-based heuristics, where we sample uniformly from the driving command situations. We have policy-based sampling strategies, where we use test time dropout to estimate the epistemic uncertainty of the model in order to be able to add more samples where the model is more uncertain. And we also have an expert-based sampling strategy, where we compare what the model predicted to what the expert would have done. And we are adding more samples if the deviation is larger. And this is, of course, possible, is easily possible in simulation, because we can query the expert at any time. Now, what happens if you apply this strategy, this data aggregation strategy, to the same data distribution? You can see that over time, over the iterations, we get a much less skewed and much more uniform distribution over the different aspects of driving. Let's look at some experiments. Again, we use the CARLA no crash benchmark, in this case only the dense setting, with this very challenging setting with 220 agents. And we compare it to various baselines with and without additional data augmentation. There's an additional way to do data augmentation in CARLA, which is by adding little perturbations to the actions to have the expert force the expert to drive back to the towards the road. But in order to observe slightly, left and right of the road, you can add these perturbations. And this is what we found. So here's a plot over the iterations of data aggregation for different data aggregation strategies. And we compare this to the expert performance, to CARLA with these action perturbations, and default CARLA. And what you can see here is that data augmentation increases the performance of all methods. However, Dagger quickly overfits. For instance, here in Cyan, Dagger increases in performance but then drops again, while the proposed model DARB plus, for instance, here in yellow, continuously increases in terms of performance, and an ensemble version of our model performs even slightly better. Significantly or remarkably, the new data augmentation strategy, which is really independent of the model type, can be applied to nearly all imitation learning models, significantly reduces the number of collisions with dynamic objects, as you can see here. So we have this CARLA as baseline, and then in green, what happens if you use this model in combination with this proposed data aggregation strategy. And you can see that in particular for dynamic objects, we get a significant reduction in terms of collisions with these objects. However, we also obtain more timeouts. So this statistics is of course influenced by the fact that we have less collisions, because now, due to the fact that we have very dense scenes and the simulation just gets stuck sometimes, this is a deficiency of that version of the simulator, we are also stopping more often effectively and waiting for clocked scenes to become unclocked, or waiting for red lights to become green. So we get more timeouts, more penalty for timeouts. Another important thing that we notice is that with this variant of Dagger, we obtain a significant reduction in the variance compared to CARLA and original Dagger. This is again the variance with respect to random training seeds. So we just changed the random number generator for training different variants of the model. You can see that, for instance, Dagger, after its third iteration, achieving a success rate of 17.8, has a very high variance of 3.6, which is usually not reported in research papers, but it actually should, because this makes a significant difference in terms of the results. On the other hand, our method is able to further improve upon this number, the success rate number, and at the same time enables a significant reduction in the variance at test time. We also looked at what our approach attends to using GradCam as a attention visualization technique. And so here on the left we see, for the same scene, the visualization of the attention map of CARLA and our approach on the right. You can see that our approach attends correctly to the dynamic objects and to the traffic light in the case of the second example on the bottom. And finally, I want to show you some video here as well. So we see a side-by-side comparison of CARLA and the Dagger variant that we have proposed. You can see that it, for the same situations, stops correctly, doesn't run over traffic lights or pedestrians, doesn't as easily collide with vehicles because it is trained on a more balanced data distribution. Okay. Another aspect of this end-to-end driving problem is the intermediate representation that we should choose. So far, we have looked at models that were very monolithic and didn't use a particular intermediate representation. But in the past, it has been shown that these intermediate representations are actually helpful. So rather than, choosing a modeler pipeline or a end-to-end learning approach, we're now looking for something in between that's neither as complex as a modeler pipeline that's composed of many small modules, nor a single monolithic approach, in order to incorporate knowledge about computer vision process into the self-driving policy. And we are not the first to do this. This has been done before. There are several papers about this, such as this paper by Zhu et al. That ask, well, does computer vision matter for action? What they did is they analyzed various intermediate representations, such as semantic segmentation, depth maps, normal maps, optical flow, and albedo. And they found that for various tasks, such as urban driving and off-road driving, intermediate representations actually help in improving results and robustness. They observed consistent gains across simulations and tasks. And they found that depth and semantic maps provide the largest gains depending on the type of task. And this is the setting that we're considering here as well. So we're somewhere in between. We have now a neural network that predicts an intermediate representation, and that intermediate representation then goes to a vehicle controller that predicts the action. The question is, of course, what intermediate representation should we choose? Semantic segmentation, bounding box, depth, or optical flow. In this study here, we focus primarily on semantic segmentation, as it has been found in a previous study to be one of the most important intermediate modalities to be predicted and to gain most robustness for the self-driving task. So first of all, well, what is a good visual abstraction? First of all, it should be invariant. It should hide irrelevant variations from the policy. It should also be universal. It should be applicable to a wide range of scenarios. It should be data efficient in terms of memory and computation. And it should be label efficient. It should require little manual effort. And these last two aspects are what our paper focuses on. This is something that hasn't been investigated in depth in the past. And we're trying to find an intermediate representation that's not only leading to better generalization and more robust driving policies, but that's also cheap to obtain, that's easy to obtain, that's data efficient, and that is label efficient. Yeah, so semantic segmentation, what we focus on here, encodes task-relevant knowledge, such as the road is drivable, and semantic priors about grouping, and can be processed with standard 2D convolutional policy networks. However, the disadvantage of semantic segmentation is that it's very time-intensive for labeling. For instance, in the case of cityscapes, the authors reported that labeling a single image with per pixel semantic class labels takes about 90 minutes. So this is the setup that we consider. We have a segmentation or detection network here. So we use actually a combination in our approach, combination, investigate both semantic segmentation and 2D object detection. And this segmentation and detection network A predicts this visual abstraction, semantic label map, and the detection map from the input image. And then we have a conditional imitation learner, which is implementing our controller that takes this visual abstraction and predicts the action. And so we have these two things. We have the visual abstraction network A and the control policy pi, and both of them are neural networks. Pi additionally depends also on the velocity and the conditional command, of course. And composing both of these together yields the final driving policy. For training, we assume that we have a dataset with ns images, a small number of images for which we have semantic labels available. And then we have another dataset with images annotated with expert driving controls. And that dataset is much larger because it's much easier to obtain. We just need to drive around to get that dataset. So we assume NS is significantly smaller than NC because this requires manual labeling effort, while this one here just requires driving around. And then what we do is during training, we first train the visual abstraction network using the semantic data set, and then we apply this network to obtain the control data set, and then train the control policy using that control data set. And so we pre-process the inputs of this control data set using the visual abstraction network to create a data set of abstraction and control pairs on which we then train the control policy using the control data set. Now what we found, and this is shortening the results of the paper to a single slide here, is that we can obtain the same or even better performance in terms of driving success rate with at the same time a significant reduction in annotation time. On the left, we have used a dataset of 6,400 finely annotated images of 14 semantic categories, where the corresponding annotation time would be 7,500 hours. I'm saying would be because we are testing this in the CARLA simulator, so the semantic segmentations are for free, but in reality, you would actually have to label them manually. And we obtain a policy success rate of 50%. In the right example, we trained with 1,600 images only that are coarsely annotated with just 6 classes, and some of these classes are only labeled in terms of bounding boxes, for which you train a box detector. In this case, the annotation time is 2 orders of magnitude smaller, while the success rate of the policy even increases. And this really shows that larger semantic data sets and larger data sets with more annotations and more classes are not necessarily better. So it's important to focus on the right aspects for the driving task. Again, here in this case. Okay, and then finally, I want to give a brief overview of a very last project that we did recently on attention. The question we ask here is, well, how important is attention for self-driving? If we are doing self-driving, typically we have to combine feedback or input from multiple sensors. In this case, we considered a front-facing camera facing to like 45 degrees to the left and 45 degrees to the right. You can add also cameras in the back of the vehicle, or 90 degrees to the left, 90 degrees to the right. You can add radar, you can add LiDAR, you can add various laser scanners or sonar. So there's all these different sensor modalities that provide a wealth of information. And it's very difficult to compress this very high dimensional signal to the low dimensional action command or driving command. And the primary question is, well, how can we actually compress this efficiently? And attention is a natural way to do this, because we can force a model of lower capacity to successively attend to different regions of the input in order to make a decision. And at the same time, we were developing a new output representation that's not in the image domain, but that's in the actual physical, in our case, in the bird's eye view driving space, and makes predictions for waypoints in that bird's eye view space and for semantics in that bird's eye view space. So we're predicting both semantics and waypoint offsets using a implicit neural representation that adaptively queries the input through these attention maps. We have an MLP here that gets us input a bird's eye view query location, X, Y, and time, and then iteratively compresses this input information here into a compact vector representation C, from which we can then query semantic information and waypoint information. We use then at driving or test time, we use only the waypoints for a controller that follows these waypoints, while semantics is used at training time to guide the model, and actually turns out that it helps and adds learning. We evaluated this new model on the latest version of CARLA, which is much more challenging. This is the CARLA leaderboard version 0.910, and we evaluated on the most challenging town in that environment, which is town 0.5. By visualizing the attention maps that the model has learned, we can see that the model attends to regions in the image that are actually relevant for driving, such as traffic lights, as illustrated here. And our findings indicate that, more camera views are better. So we can use this model to efficiently encode more camera views. For instance, here going from 1 to 3, we see in the case of just occupancy prediction plus waypoints, or semantic prediction plus waypoints, both an increase in driving performance. No scenarios and scenarios are different levels of difficulty for the driving scenario. In scenarios, we have additional adversarial scenarios inserted that are more challenging to overcome. So these numbers are slightly worse. We also see that the version that uses semantics as auxiliary supervision, as in the case before, improves driving performance overall, and that also attention improves the performance. Here we have different versions of our model with different iterations of this attentive process, and we see that with one iteration of our attentive process we do better than without having this attentive process. At the same time, we found, in agreement with other related works, that using multiple frames as input decreases performance actually. And this is due to the fact, we believe, that the velocity already is a good observation that captures most of the important relevant things from the past. And at the same time, using previous frames makes it much easier for the model to learn or to causally confuse certain aspects of the driving problem, and therefore leads to decreased performance. So let me summarize briefly. We have shown that mixture models can significantly improve generalization performance. So a larger variety of different experts can be beneficial for self-driving. Task-driven optimization is a difficult problem, but it's important, and if it's done right, it can improve performance by a few percentage points. I've also shown that data augmentation is important, but it can easily overfit in the case of self-driving, unlike it does for classic manipulation tasks in robotics. But critical states and replay buffer can improve the performance of data augmentation techniques and can actually also reduce the variance. We've seen that exploiting visual abstractions leads to more robust driving models, and that a higher segmentation accuracy does not necessarily imply better driving. Furthermore, we've seen that hybrid representations are able to reduce annotation costs, and that visual abstractions can significantly lower the training variance as well. And then finally, we've shown that attention is helpful for self-driving, but it hasn't been explored much yet, and I believe that in the future we will see more and more self-driving models that use attention as well. That's all from my side. I want to thank you for your attention, and if you're interested in our research, here's a link to our blog. Thanks.